Okay, so in this lesson, we're going to be reviewing a lot of the key features of polynomial functions that we've learned in the past and adding a little bit to it. So remember, your polynomial functions of degree n can be written in the following form, and this is just a general, like, standard form, where n is a non-negative integer. That's what makes it a polynomial. So the powers that you have on x have to be positive integers. You can't have like x to the 1/2 because that's really a radical in there, or x to the -2 because that would make it a rational function. Recall types of polynomial functions are constant, which is your horizontal line, linear, quadratic, cubic, quartic, quintic, and then anything after that, we just say a polynomial of degree 6 or a polynomial of degree 10, so on. All right, some of the properties and key features of polynomial functions. The degree n is the highest power we see on x, and that's really important because the degree tells us what type of polynomial function it is. It also tells us a lot about the behavior of the function. The leading coefficient is the coefficient of the term with the highest power of x. It also dictates the end behavior of the function, which we're going to go over in a minute. Our x-intercepts are our zeros and roots of the function. It's where y is equal to 0. Our y-intercept is always the constant term of the polynomial function if it is written in standard form, not factored form or vertex form, but standard form. Remember, our y-intercept, anytime we have a y-intercept, x is equal to 0. Polynomial functions have maximum mins. They have relative maximums and absolute maximums. End behavior is what happens to the functional values, what happens to y as x approaches positive and negative infinity. Domain is our x, range is our y, and we're also going to be talking about intervals of increase and decrease on our polynomial functions. So let's first review end behavior. If you need to pause the video at any point to get some of this written down, please do. So when we talk about end behavior, we always talk about what does the left arm of the graph do? So as x goes to negative infinity, is that left arm going up or is that left arm going down? The only time it will not go up or down is if it's a constant function. Other than that, unless it's just, y equals 5 or y equals 8, that left arm or right arm will go to negative infinity or positive infinity. And then as x goes to infinity is the right arm of the graph. So we're going to start out with odd degree functions. The easiest way to relate to an odd degree function is to think about a linear function, because a linear function is definitely an odd degree function. When you have a linear function, that leading coefficient, that a sub n, is the slope. Remember, when we say it's in standard form, we mean it's the highest power to the lowest power. So anytime the slope is positive, we know that the left arm would be down and the right arm would be up. Every time we write end behavior, we always are going to say what is happening as x goes to negative infinity, which is our left arm, what is happening as x goes to infinity, which is our right arm. So as x goes to negative infinity, what is the function doing? Is going down. So we're going to say y goes to negative infinity. That means the left arm is down. And then as x goes to infinity, y goes to infinity. Again, think of that linear function with a positive leading coefficient. It would look like this. Okay, so now let's talk about if we had a negative leading coefficient. Again, think about that linear function. It would switch around. So in this case, the left arm is up and the right arm is down. Anytime we do end behavior, we're going to say as x goes to negative infinity, y goes to, and then you have to put what it does. So in this case, y is going to infinity because the left arm is up. As x goes to infinity, y goes to, and in this case, it's going to negative infinity because the right arm is down. Something that is significant about odd degree functions is the arms always go in the opposite direction. Anytime you have a linear function, a cubic function, a quintic function, or any function of odd degree, the arms always go in different directions. In the like when you look at it goes to negative infinity and positive infinity, one arm's up, one arm's down. If both arms are going the same direction, you're messing up or it's not an odd degree function. All right, for even degree functions, it's the opposite. So if we look at quadratic functions, quartic functions, or degree 6, degree 8, any of those, the arms always go in the same direction. So if the leading coefficient is positive on an even degree function, in that case, both arms are up. think about a quadratic function. That's an easy function for you to relate to. If that leading coefficient, so the coefficient on x squared is positive, we know our parabola opens up. So let's jot that. In this case, both arms are up. As x approaches negative infinity, y would approach infinity. And as x approaches infinity, y would also approach infinity. Again, it's even degree. The y that should approach the same direction. They're either both up or they're both down. So again, thinking about a quadratic function, if it has a negative leading coefficient, we know that it opens downward. And even if it was quartic or degree 6 and it had some like humps in the middle, it doesn't matter. It's what happens in the ends. That's why it's called end behavior. So in this case, we would say both arms are down. And as x approaches negative infinity, y approaches negative infinity. As x approaches infinity, y also approaches negative infinity. All right, so what we're going to do first is we're going to describe important features of the functions below. So we're going to go through all these things that we've listed up here, like what is the degree, what is the leading coefficient. What we're going to try to do is we're going to try to list everything we can think of without the use of technology, and then we'll use our technology to find some other important features. You also have that pink checklist. You can use that. That's one of the things we use. We might not be able to do everything on there, like discontinuities and stuff like that, but we can use that to make sure we are listing our important features. So let's talk about what we know without the use of our calculator. The first thing I recognize about this, it is in standard form, and the highest power I see on x is 3. So that means that the degree of this function is 3. The leading coefficient on that leading term is also 1. So I'm just going to call that, you can put LC, or this time I'm going to write it out, leading coefficient. But if you ever see me write LC, that means leading coefficient. So we have an odd degree polynomial with a positive leading coefficient. So guys, I immediately know my end behavior. As x approaches negative infinity, y, or let me write f of x in this case, because that's what the name of the function is. F of x will also approach negative infinity because the left arm should be down. As x approaches infinity, f of x will approach infinity because the right arm should be up. Anytime you have an odd degree polynomial, positive leading coefficient, left arm's down, right arm's up. All right, other things that we know about this function. If the degree is 3, then that means the maximum number of zeros that it can have is 3. The maximum number of times it could cross the x-axis is 3 times. And if the degree is 3, and let's say it did have actually 3 real zeros, the maximum number of turning points this could have would be 2. So the maximum number of turning points, and y'all, your turning points are your maxes and mins, is always 1 less than the degree. It doesn't mean it'll turn that many times. That's just the maximum number of times it can turn. We also know the y-intercept. Because this is in standard form, the constant term is always the y-intercept. So we know the y-intercept is -7. Also, think about it, folks. If you were to substitute 0 in for each of these x's here, all of these terms would end up turning to 0, and you would just have left -7. Because this is an odd degree function, and we know that polynomial functions are continuous for the domain of all real numbers, and one arm's up and one arm's down, we also know our domain and range. Our domain is all real numbers, negative infinity to positive infinity, and our range is also all real numbers, negative infinity to positive infinity. Okay, folks, those are the things that I can tell you, and you should be able to tell me about this function without having to graph it. And this is where we need to work towards, and this is stuff that you learned last year. Now what we're going to do is we're going to graph this function. You can use Desmos or your graphing calculator to graph it. Graphing calculator, we're going to type this into y equals. I'm going to real quickly go to zoom at the top and go to zoom standard because I have no idea what the window was the last time. And in this case, I can clearly see this cubic function here. If I couldn't see some of the max and mins or zeros, I would have to play with my window to fix it. So just to recall, to get your maximum or minimums, you're going to go second trace, which is calculate. Let's say I want to work from left to right, so I want to get that maximum first. So I go down to maximum, press enter. Your calculator is not smart. You have to tell it what to do. So I'm going to go to the left of that maximum, press enter to get the left bound. Go to the right of that maximum, press enter to get the right bound. Then when it says guess, if you'd like, you can guess about where it is. Press enter, and bam, there's our maximum. Go ahead and write that down to, normally I say 3 decimal places, and we should, but for what we're doing right now, just at least round it to 1 decimal place. Then recall to get your minimum, you would do the same thing. Second trace calculate, go to minimum, press enter. Of course, this time we want the minimum, so to get to the left of the minimum, that would be on the left side of it, press enter. To get to the right of the minimum, that would be on the right side, press enter. And then if you'd like to guess, you can, or you can just press enter and it'll give it to you. And make sure you write that down. On your paper, draw a little sketch of this, label those maxims. Other key features we want to know about this graph are the x-intercepts. Turning points, which are our max and mins, and our x and y-intercepts are extremely important when we're trying to describe a function. So the first thing I'm going to do is go to my table and see if I can recognize any of my x-intercepts on the table. And so when I'm looking at the table, if I look to see if there's any values of 0 in the y, I can see right here that -1 is an x-intercept. But I also know I have an x-intercept between -4 and -3 because the range values go from negative to positive. So we're going to have to use our 0 command to get that. So I'm going to go in the calculator. Let's say I work left to right. So I'm going to have to scroll all the way over here and get to the left of that 0. So I'm a little to the left of that x-intercept, press enter. Go a little to the right of it, press enter. And if you want to guess, you can. I'm just going to press enter. And we can see that that 0 is -3.828. And then do the same thing for this most right 0, this third one over here, so that you can get it because we could not get it out of the table. And write that down on your paper. Okay, so we would call these max and mins relative maxes and relative mins because they're not actually the highest point or the lowest point on the graph. Because since this graph actually goes off to negative infinity and positive infinity, it doesn't have an absolute max or an absolute min. And then we write down our x-intercepts. All right, so the next thing we're going to do is we are going to talk about where this function increases and decreases. And that's why it's really important for you to find the maximums and minimums first. Wherever our turning points are, that is where it changes whether the function is increasing and decreasing. So if we look at this from left to right, think about if you were driving in the mountains or something. Going from left to right, the function is increasing from negative infinity to -2.6. Now I know that's weird because sometimes students have a hard time writing these because they want to write it for the range and not the domain. But make sure you're writing it for the domain values. Then between -2.6 and 0.6, it is decreasing because we're going back down. And then from 0.6 all the way to infinity, it is increasing. So to write our intervals of increase and decrease, I'm just going to put right here, INC for increasing. We want to write it from left to right. We would say this function increases from negative infinity to -2.6 in union with 0.6 to infinity. Make sure you use parentheses and not brackets, because when you're actually at that maximum point or this minimum point, you are neither increasing nor decreasing. That is the one point on this graph, or 2 points on this graph, where the rate of change at that instant is 0. So that's why we put the brackets there. Then for where it's decreasing, we would say it's decreasing between -2.6 and 0.6. Again, make sure anytime you give intervals of increase and decrease, you do it for the domain values, so for the x values, not for the range values. That's a common mistake that I see students make. All right, I would like for you to pause the video and do the next one on your own. Now, folks, if you're just waiting and writing all this down and you're not practiced doing this stuff in your calculator and pushing yourself to learn this, you're not going to be successful on your assessment. So make sure you actually pause and to try this on your own. Pause now. Okay, so in this case, we have an even degree function, and the degree of this is 4. The leading coefficient is -2. So since this is an even degree with a negative leading coefficient, we know that both arms end up down. So as x approaches negative infinity, f of x approaches negative infinity. As x approaches infinity, f of x also approaches negative infinity. The maximum number of zeros this function could have is 4. The maximum number of turning points this function can have is 3. And the y-intercept, because this is in standard form, is 4. We know the domain is all real numbers because it's a polynomial function. But in this case, we do not know the range yet because we know that it doesn't go to infinity like the last one. This one's going to have an absolute maximum somewhere since both arms end up down. So we're going to have to use our technology to graph that and find those max and mins and our x-intercepts. So go ahead, if you haven't done that, and do that. So when we graph it, we can see this one actually has 3 turning points, 2 maximums and 1 minimum. So we want to make sure we have those and write them down. These maximums are absolute maximums. They're the highest the graph goes. So that's why the range is from negative infinity to 8.5, including 8.5, because it actually reaches that point. And then we need to get our x-intercepts. This one actually only has 2 x-intercepts. Remember, it could have up to 4 x-intercepts, but that doesn't mean it has 2. So since it only has 2, what that means is 2 of them are real and the other 2 are imaginary. All right, in this case, when we look at it, this function increases, decreases, increases, and then decreases. So we have to talk about all those parts. So in this case, we're going to say that the function is increasing from negative infinity to negative 1.2 in union with, and then it increases again from 1.2, from 0 to 1.2. So again, if you kind of mark this off, here's the different intervals. And so I'm looking for the intervals where it was increasing here, and it was increasing here. And you always write it for the domain values, not the range values. So where is it decreasing? It's decreasing here and here. So we're going to say that this function decreases from negative 1.2 to 0 in union with 1.2 to infinity. The number of times a given polynomial function has a factor is the multiplicity of the related root. A multiple root occurs when a polynomial equation has a root with a multiplicity of 2 or greater. For example, f of x equals x plus 2 squared times x minus 3 cubed has a double root at negative 2 and a triple root at 3. If you were to write this out in completely factored form, you would see x plus 2 is a factor twice, so you have that 0 of negative 2, and x minus 3 is a factor 3 times, so you have that 0 of 3. Without having to multiply this out, I know that if I have 2 linear factors here and 3 linear factors here, that the degree of this polynomial would have been 5. So I know this is an odd degree polynomial. I also know that if I was to multiply this out, that the leading coefficient would be positive because none of these x's have negatives in front of them. So if it's an odd degree and the leading coefficient is positive, I know that the left arm would be down and the right arm would be up. And I don't have to multiply that out to put it in standard form to figure that out. All right, I also can figure out the y-intercept. Now in this case, it's not in standard form, but remember, if you wanted to find the y-intercept of a function, all you do is substitute 0 for x. So if I come right here and I substitute 0, that's 0 plus 2 squared times 0 minus 3 cubed. Well, folks, that's really just saying 2 squared times negative 3 cubed. So 2 squared gives us 4, negative 3 cubed gives us negative 27. 4 times negative 27 would be negative 108. So therefore, without doing any work, I know that the y-intercept is at negative 108. And of course, we already talked about the x-intercepts up here in the directions. So what I would like for y'all to do is I want you to go through and do number 12, A through E. So for each one, you're going to state the degree, the leading coefficient, the maximum number of possible zeros, the maximum number of possible turning points. You're going to do the end behavior, state the y-intercept. And if you know the zeros, go ahead and state them. If it's one where you can't find the zeros without using technology, then just leave it alone. But at least do that part. And then we'll be reviewing that tomorrow in class. And then after you do that, using your graphing calculator, I want you to find the real zeros, the relative max and relative minimum points, and the intervals of increase and decrease for the functions in A and B. So you do not have to do all of these. just go back and do that part for the first two functions right here, for f of x and g of x. And then we will talk about question number 4 together in class. And we'll do the practice in class. So make sure you complete number 2 here and number 3 before coming to class tomorrow.